Okay, perfect. We are now in YouTube. Welcome, everybody. Thank you for coming one more week. And today it is a pleasure to introduce you Dr. Teresa Antoja from the IEEC-ICCUB of Barcelona. Teresa is... I think I have... Sorry, yeah, it was the YouTube. Teresa is an expert on the dynamics and kinematics of the Milky Way disk, but she also studied many properties of the Milky Way, from the stellar streams in the halo to other structures like the effects of the bar in the solar neighborhood. And she's also inside the Gaia collaboration, working hard in the publication of the new results in the Gaia DR2 and EDR3. That is something that she's going to talk today. Teresa did his PhD in Barcelona under the supervision of Francesca Figueras and Octavio Valenzuela. She presented the PhD in 2010. And after that, she moved to Groningen to work with Professor Amina Helmi to continue this work on the study of the kinematics and dynamics of stars, in this case, more in the halo of the Milky Way. After that, in 2013, she moved to Norway to work as a ESA research fellow in STEC. And after that, she went back to Barcelona to work as a Maria de Maeztu postdoctoral fellow. That was then converted to a Marie Curie individual fellow in 2018. And finally, now this year, or I don't know if it was 2020, she got the Ramon y Cajal postdoctoral fellow. That is the fellowship she's having now in Barcelona. So this is the very short summary of Teresa's CV. I know that there are many more things that can be highlighted on his CV, but Teresa, if you have something that you want to add that I missed, please do it freely now in talk, and you can start as soon as you want.
It's fine.
Again, thank you everybody for coming, and thank you, Teresa, for accepting the invitation.
Thanks to you for the invitation, and thanks to everybody coming here today. It's a pleasure to present this knowledge that we have of a perturbed Milky Way, thanks to the Gaia data. So, okay, now I need to start again for some reason, because it's not advancing. Okay, I left it too many. Yes, now, so this story starts with a spiral shape that was detected in the Gaia data 2018 when we first saw the data, and that after some modeling let us know or uncover that there was a strong perturbation of our galaxy some million years ago. And I'm going to show how this, very briefly, how this discovery was done, and some follow-up work on what we think that is probably the cause of this perturbation, most likely the Sagittarius impact in one of its past pericenters. This is a bit the outline of my talk. I start with a brief introduction. Don't want to forget mentioning all my collaborators. In general, all the IPAC, the Data Analysis Processing Analysis Consortium of the Gaia mission, that of course makes possible all these exciting discoveries. Our group in Barcelona, which is quite large, you have here in the middle, with scientists and engineers working directly on the processing, and a few collaborators that have here in the bottom line. Okay, so let me start with this image, which I think it's one of the most wonderful and meaningful images in astronomy, which is this Hubble Ultra Deep Field, showing all this variety of galaxies with different shapes, different colors. And of course, one of the questions that comes to mind when you see these images is, how do galaxies form and evolve, which has been identified as one of the important questions in modern astrophysics, that one can try to answer by studying these galaxies at different redshifts, or alternatively can be studied with our own galaxy, the Milky Way. This is the view that we had of a complete galaxy a bit before Gaia. This is made of a composite of images from Earth. And of course, it's not that easy in our case to infer from what we see in the sky because of our location inside the disk of the Milky Way. It's not that easy to infer the structure of the galaxy as a whole. We've done some work, of course, and we can now tell, obviously, that the galaxy is a disk, and that's why we see this band on the sky. Most of the stars are rotating in this flattened disk, presumably surrounded by this dark matter halo. And seen face on, our galaxy could look something like this. This is an artist's impression, obviously. We know certainly there is a bar in the center, some spiral arms that for sure must be influencing a lot the orbits of stars and the star formation processes, for instance, in the galaxy. But yet this is another of the big unknowns in modern astrophysics, the dynamics of the spiral arms. And in the case of our galaxy, even how many of them there are, if there are differences in different populations of the gas, for instance, something that is really, really quite unknown. And of course, in the context of what do we think the processes that have higher influence on the history and evolution of the galaxy, we have to keep in mind that the galaxy is not alone in the neighborhood. It's surrounded by dozens of other galaxies, dwarfs and not that dwarfs, that are meant to merge with the central galaxy, our own, in the future, as we know from simulations of galaxy evolution and hierarchical growing of galaxies. In the case of the galaxy and how do we study galaxy evolution, the important or the different thing compared to other galaxies is that we can have individual measurements of quantities of stars in galaxies. One of or some of them are the velocities on the individual stars in the disk. I'm showing here a bit of a representation of the coordinate system I'll be using, cylindrical coordinates, so Bz, how the stars move up and down, B5, how they rotate around the center, and Br, their radial in and out motion. The importance of these velocities, or in general positions and velocities phase space, is that they allow us somehow to do a kind of diagnosis of the Milky Way, its current state, but also what happened in the past, if these velocities still retain some of the memory of the memory of past events. For instance, to give an example, and this is known since the arrival of very large spectroscopic surveys complementing proper motions already existing, for instance, with the IPARCOS mission. And one of the interesting results that came at the time was, for instance, here in this plot, left plot, the vertical velocities of the stars as a function of Z, showing some kind of wiggles, while we would expect exactly a mean zero vertical velocity in a disk, because we should have the same number of stars moving up or down. Otherwise, it's a very strange disk. And that is exactly what was found, or even more complex patterns of the vertical Bz velocity as a function of Z and R, where you see this kind of cross patterns in velocity, while I repeat, this should be zero everywhere in the galaxy. This allows you to make this diagnosis, for instance, if there has been external perturbation going on, or in the same way, if the spiral arms and bar have perturbed significantly the orbits in the disk. So this diagnosis, or this process of inferring current structure and past evolution of the galaxy has been going on for years. I just think that with Gaia, we have somehow put this in another level of detail. Very briefly, I will introduce Gaia. I'm sure you know already a bit about it. This is the satellite. You can see here the relative size that is there already in the sky, in the L2 point, scanning all the sky, so turning around and around and detecting all the sources many times with these CCD detectors that you have here and the time they were being assembled. Also the photometers and the spectrographs, these are the different instruments on board. And more important for this talk is what Gaia retrieves from all these measurements. In the detectors, the full astrometric solution that returns as positions in the sky, parallaxes, proper motions, also magnitudes, other magnitudes in different bands, and very important for what I'm going to explain, radial velocities. because these are not measured for all stars, only for the brightest ones that Gaia detects, but it's the key ingredient that complements all the astrometric measurements and allows us to have 6D phase space coordinates. So the 3 positions, the 3 velocities, and that is the best sample. It's really a treasure for doing this kind of diagnosis that I'm talking about. Okay, so very briefly, this was the sky as saw before Gaia in the map released in 2018 after DR2, where we see a lot of details and playing with different photometric bands. You can get this sort of very interesting images. And finally, the last release, which was in December 2020, so half a year ago, where the release image was not anymore an image, and it's now a movie where you can see the prediction from proper motions, the prediction of the movement of stars 2 million years into the future, as measured by Gaia. More important, maybe for our talk, is to see not the sky projection, but the extension of the galaxy we are covering, and we are having measurements right now. So this is, and it's even a bit exaggerated, this black circle would mark more or less the position of the galaxy where we had a significant sample of 6D phase space stars, so all the coordinates. A bit better when different this rave or slow and spectroscopic surveys came out around 1 kiloparsec size region. And now what we have with Gaia, this is the extension that we are covering with 6 million stars, while before we used to have like order of 100,000. And more important than that, with precisions in velocities of the order of the kilometer per second, while it used to be something like 10. I think that's exactly, I mean, this improvement on the precision is exactly what made us find these interesting discoveries, and that it was like putting or using the correct glasses for the first time and starting to see things that were not seen or that were blurred before. And this is the example of the phase spiral. This is the vertical projection of phase space, so Z, the vertical coordinate as a function of the Z, how they move, the velocities, how they move up and down. And we are comparing before DR2 and after DR2. You can see here this shape of spiral that if you apply some kind of masks, maybe done by other authors, you can see much clearer here. I always tell that I have to admit that when we first saw this in the data, we were thinking there was a problem because this was totally unexpected, and it looked like correlations between Z and BZ that were not predicted by any models, so we were a bit surprised. But after ruling out any kind of systematics and after going into modeling, that in the end we find that it made total sense that this was a true thing. Also, when painted, this same projection, when painted as a function of BR and B5, the other velocities in the plane of the vertical ones, we see even more surprising things, like again this spiral shape here becoming very clear. And so to understand, and I go very briefly with that, to understand a little bit what can cause this spiral, we need two ingredients. First, to understand how the orbits, vertical orbits are in the galaxy. Of course, they are oscillating with Z, and in the diagram ZBZ, each star is doing a revolution around the center with the corresponding points, of course, the turnabout points of the orbits. And it's important to know what is the period of revolution, so to make a whole circle in the oscillation for each stars. And it has a double dependency in our galaxy. First, it depends on the radius, so the farther away they are from the center, the longer it takes to do a whole revolution, and also for the amplitude. So let's say a star that is oscillating with a higher amplitude, it goes farther from the plane. This will take longer times. This is similar to an anharmonic pendulum, where the correspondence would be the length of the core, and again the initial amplitude that will determine completely the period. Another ingredient that we need is to think about external perturbations, and we are seeing here an edge on disk perturbed by this red galactic satellite that is orbiting around, and especially in the outer parts of the disk, we see many of the stars of the main disk being scattered through higher Zs. So if we go now to this projection again, in a normal galaxy, in equilibrium, we would expect to have the same number of stars, or an isotropic distribution, basically here. We should have the same number of stars up and below the plane, and the same number of stars moving up then down. So this should be uniform. But if one of these perturbations has happened, as we saw in this movie, that some of the stars were displaced, for instance, displaced to negative Zs. So you start from the starting point with your whole sample is suddenly displaced in Z. And you let this system evolve because the satellite now, the galactic satellite, this other galaxy has left, is far away now. And each of the individual stars will start doing its revolution, but with their own period, depending on the radius and the Z, the total amplitude they have. So if we now let this evolve with time, we see that the outer parts, as I said, take longer to do a whole revolution. So they will start to be left behind. And in the end, this now goes faster. This will turn into a curl shape that is very similar to what we see. The interesting thing that we realize after joining these pieces of the puzzle is that the more curl this is, or the more winded this is, the longer time it means that the longer time it has passed since the beginning or the spark of this perturbation. And this in practice means that if you can measure the difference of two of these consecutive turns of the spiral, and you know, or you can approximate a little bit how the frequencies of the stars in our galaxy are, using this very, very simple formula, you can know where was the time that this process that we call phase mixing process in physics started. And this gave us something like 300, 900 million years ago, which matched very well the last or the previous pericenter passage of the Sagittarius dwarf galaxy. This made total sense. It's a quite massive galaxy, relatively nearby, that had a pericenter exactly around that time. There is some uncertainty in our prediction and also in the prediction of the pericentric times in different models, but they seem to match very well. So apart from telling us this discovery that the Milky Way had this strong perturbation in the past, and that is still recovering from it, it can be used also as a way to constrain the perturber orbit, in this case Sagittarius, for instance, their mass or their time of the pericenter. So this opens up a new world. After the discovery, some people look at the simulations that they were already in place, particular simulations tailored to mimic the effect of Sagittarius approaching the Milky Way, and they saw, as you see here in this bottom row, that they found exactly what we see in the data, not exactly, but qualitatively at least it matches. So our explanation of the Sagittarius perturbation made sense. I must say, though, that there have been alternative proposals for this. For instance, the bar buckling created some vertical instabilities as well. Some bending waves, perhaps induced by the multiple interactions with dark satellites, could be also a possibility. And so it's true that this is not totally settled. We need to investigate a little bit more. There are other uncertainties, like if this is a simple phase mixing process, as I've shown, or it has some self-gravity. It's unknown whether the gas would be, for instance, affected similarly as the stars. So to answer this and other questions, we started this process with Santi and Begoña, who are here in the audience, and as part of one of the University of the Complutense PhD thesis, where we went to cosmological simulations to answer all these questions. The previous simulations and body ones were very simple in the sense that there are only, first gravity, no gas, anything else, and one single perturber. We are now studying this in a more complex but realistic at the same time simulations where we have gas, star formation, different perturbers that you can see here in this box. So we are looking at the central galaxy that you can see here in a zoom in, but you can see already a lot of perturbers here. So this for sure is going to be more complex. And yes, so we divided this disk in different regions and different azimuthal regions, and we try to investigate if we see some sort of phase spiral in this vertical projection ZBZ. Well, and the answer is yes, we were very surprised. It's true that this is one of the simulations of higher resolution, cosmological ones, I mean. So, okay, if there were some chances, it would be with this kind of simulations. And you can see here that this is true. These are these 12 azimuthal regions as a function of time. And we see here that at least in a certain part of the evolution of this galaxy, we do have some spiral shape in each of the little neighborhoods that we are studying. But not only this, if we now study the whole evolution of this simulation of this galaxy, we see basically that this sort of distortion, spiral distortion, is present at most of the times. And that is not surprising because we have several perturbations, different pericenters, and sometimes there has not even been time to completely relax from the previous pericenter that there is a new interaction. So this was very, very surprising. There are other interesting results. You can ask Begonia, and we hope that the paper is soon out. And one of the things we would like to look with the simulations is the effect on gas of these perturbations. And I'm saying this because there is already growing evidence that even for our Milky Way, there have been some star formation peaks at certain times, star formation enhancements that surprisingly or not that surprisingly coincide with the estimated pericenter passages of Sagittarius. Not just the previous one, as this one here, but also previous pericenters. So we are seeing that these kind of events of perturbations are very important, not only in terms of orbital perturbations, but also other general processes like star formation, which makes sense, was expected. But I think it's very nice that we are seeing confirmation. And by the way, I didn't mention, but this comes also from Gaia data, in this case, not orbital, not velocity data, but color magnitude diagram fitting with models done by Tomás and Karma, who is also in the audience. Okay, so more implications of the phase spiral. Maybe one that is not that nice is that I think it's now clear after this thing that modeling the disk of our galaxy as something axisymmetric and time independent is totally incorrect. Because we see the galaxy is not in equilibrium, is doing all these phase mixing events or even self-gravitating waves, which would make even worse. And one of the implications is, for instance, that some classical modeling, like Jean's modeling, where we used to remove all the terms depending on time or in azimuth, well, this is not very correct. We were thinking that it could be a good approximation, but in the end, it's not, as for instance, this group shown with simulations. This is purely simulations, and they were applying Jean's modeling to detect or to quantify the amount of dark matter as a function of Z in their disk, in their simulation. And you see here the orange curve is the true amount because it's a simulation, so they can know the exact amount of dark matter. And the points are data, and you can see that data from the simulation, so the measurements after Jean's modeling. So you can see that depending on where you look in the galaxy, these two figures are different azimuths. Sometimes it's okay, your Jean's modeling retrieves very well your amount of dark matter, but sometimes it's quite overestimated, and by a lot. So this means that these methods have to be revised. There is kind of some hope because the same way we use the spiral shape to know the time of the perturber, it can also be used to do some fitting of the potential without using Jean's equations and using the fact that this curling, this winding of the spiral has also something to do to the frequencies, the orbital frequencies, and the orbital frequencies are related to the potential of the galaxy. So there is people are starting to find new ways to take this into consideration and use it in a positive way, in this case, to make a constraint of the potential. Okay, so, well, if the consequences, let's say, for the Milky Way were already important, as I hope I communicated successfully, I would say the consequences for the Sagittarius dwarf have been even worse. As you know, when these satellites come into the main halo, in our case, the main halo of the Milky Way, they get totally disrupted. And one case is the Sagittarius stream. Here you have where the main galaxy is right now, which, by the way, is close to the pericenter right now. So it must be having already some effect, perhaps in star formation. And you can see this stream of stars that is consequence to these tidal perturbations that the dwarf feels when entering the halo. This stream, for sure, is known for a long time, but we've done some recent work with Gaia data, where for the first time we're detecting this very huge sample of stars in the stream, completely unprecedented. This is work done by former PhD student in Barcelona in our team. And not only this, but also to measure for the first time what's the proper motion evolution along the stream. So you have here a coordinate that it's lambda, that is simply a coordinate that is oriented with the orbit of the stream. And you can see very nicely this detection of the evolution of the proper motions as a function of position. And this is very important because it's the first time that it has been measured such a longitude along the sky for the stream. There were a lot of radial velocity measurements, but not proper motions. And it's important because you can use this to constrain models of the orbit of Sagittarius, because the stream must somehow follow this orbit. And if you can do this, basically you can constrain the whole potential of the Milky Way. We are here comparing the data. This is a map of residuals of proper motions, comparing data and the most famous model, Lowan-Majewski model of this stream. And we can see some regions with strong discrepancies that points out that these models need to be improved somehow. And there has been recent work that when we add the effect of the LMC in the fitting of this orbit, this can help. So of course, the more data we know, the more ingredients need to add to explain, because we see very fine details that were unknown before. Okay, I'm gonna just say very briefly some conclusions of this first part. Milky Way was perturbed, very likely by the Sagittarius dwarf galaxy, some 500 million years ago. We can constrain the perturbed orbit and mass and possibly potential of the Milky Way by using this disturbance, this symptom that we see in phase space. Definitively Milky Way out of equilibrium, and this represents a challenge to classical dynamical model, but we are on it, and there are already examples of success of this. I'll talk a little bit, sorry, about other disturbances measured by Gaia. I move now to a different projection of phase space. So we go from ZBZ to another one, which is here radius, where they are with respect to the center of the galaxy, and B5. This plot starts at 8 because this is recent work that we did in one of these performance verification papers that came out with this early data release 3 last December. And it's just a sample. We use a sample looking at the anti-center of the galaxy. So looking outside, and that's why it starts at solar radius, and we explore what happened in the outer parts, which are very interesting because are the parts that will be most likely perturbed, for instance, by external satellites. We see in this projection, B5R, that the stars are somehow organized in this kind of diagonal ridges. And maybe it's a bit hard to see here, but again, we can use some mask, some sharp mask to see where the structures are. And we see here now much better all these gray structures. In color, you have their extension as discovered in DR2. So it means now that with this better data that has improved parallaxes, improved proper motions, for instance, proper motions have reduced their uncertainty by a half in this release. So this mostly allows you to go much farther away. So each of these diagonal ridges already discovered are now seen even at farther distances, and we even detect new of these ridges here. So the initial idea proposed after this discovery is that these ridges of stars are orbits, or are stars trapped in resonant orbits. Resonant orbits occur when the natural frequencies of the orbiting stars, in this case in the plane, so the kappa and omega, the frequencies of rotation and oscillation, when they are commensurable a pattern speed or the frequency of the bar, for instance, or the spiral arm. So this, for some reasons that I don't have a lot of time to explain, this sometimes causes a preferential orbit. So the stars would be trapped and librate around this periodic orbit. So there will be many of them, and each of these ridges would be one of these trapped structures or trapped stars in a particular orbit. And again, maybe the explanation didn't convince you very much. I can show you a model by Francesca Francudi, where with an M-body model that has a strong bar, they look at exactly the same projection, B5 radius, and you see these ridges appearing very similar to the data. And once you select one of them and you do frequency analysis, because this is a simulation, so you can really measure the frequencies of the stars, something that is not possible for the data, unfortunately, you can see that when you look at this particular ridge selected here, you see a peak of stars that have this relation between the own frequencies and omega p, which is the pattern speed of the bar, the frequency of the bar. You see that this ridge mostly corresponds to stars trapped in one of these resonances, that is the outer limblad resonance. So that was totally a possible explanation. Another one, though, and which complicates things, is that when you look at simulations where you also have external satellites and no bar, no spiral arms, you look at the same projection and you again see very similar ridges. The higher the mass of the perturber, the stronger these ridges, which makes sense. But it means that there are other processes that can create this. And given the large number of ridges that we detect in the data, it's very likely that we are having different processes here going on. I can even add a third one when we have a disk where there is transient spiral structure. If the spiral structure is stationary, we will have a similar thing as here, resonances. But if it's not, if it's transient and you have these spiral arms that sometimes are seen in simulations, well, most of the time actually, you will also see these ridges appearing. So we do have a complexity here of phenomena playing a role. And now it's our job to try to figure out if what's the dominant if we have all of them at the same time. And a complication that I would say arrives here at this point is that, well, we know in external galaxies that when you have two galaxies interacting, it's very likely that you induce bars and spiral arms in those galaxies. So I'm not sure if these three different processes are totally unrelated, or they can be even related, because you have a perturbation from a satellite, you somehow induce bar and transient spiral structure. So you have all the things happening at the same time, and not by coincidence, but by true reasons. Let me check the time. Okay. Maybe I can show this plot here. Another result from this Gaia collaboration paper from last December, where we don't look now at the whole distribution of stars, but we look at the average. So average B5 as a function of radius, average BZ as a function of radius. And let's look, for instance, at the right one. The black curve is for the whole sample. Again, is the sample looking at the anticenter. That's why it stars at A. And we see these oscillations that were already known, let's say, up to here, or more or less here. And now we are able to trace much farther away. But maybe more interesting than that is to separate stars that are below or above the galactic plane. And we see that the symmetry is completely broken. So even in B5, so we have that stars below the plane in blue are doing a faster rotation in B5 and higher positive vertical velocities, and somehow the other way around. So we are here in front of a very complex pattern, orbital movements that have velocities correlating, and you can see here how many coordinates of phase space are involved in this kind of disturbances: BZ, R, B5, Z, and most likely all the rest. So we are finding with Gaia all this very complexity, the high complexity of these patterns that we want to investigate, that we need to understand, and then investigate the causes. Most likely all of this is related also with the phase spiral, with these diagonal ridges I've shown, but we really don't know yet how exactly. Okay, let me see, maybe I will, I can skip this. So as a general conclusion of these other disturbances, apart from the complexity that we are seeing, is that most likely both external and internal, meaning perturbations by galactic satellites or spiral arms bars, both must have a role. The question is, can we disentangle the two? Or perhaps the question is, are spiral arms and bars excited by external perturbations in the case of our galaxy? Something that needs to be investigated. Some final remarks about the future. Now, this is not a work of mine directly, but I think it's worth mentioning. This Gaia HERA is really amazing, because we are, of course, doing all these very nice discoveries. And okay, I've shown these processes from velocities. We try to infer the structure or the past about our galaxy, but you know, using chemistry, using other quantities of individual stars. Recently, people have managed even to uncover past perturbations. So Sagittarius is possibly the most recent case, but there have been for sure interactions with other galaxies in the past. And there is this very nice plot showing the Milky Way here in the center and how it has evolved in mass and the different events that occur at different times, which is here the vertical axis. And so we are basically now building the family tree of our galaxy and locating all the different galaxy or progenitors that merge with our own. And I think this is simply amazing to be able to go that back in time and discover mergers like Gaia Enceladus that are believed to be about 10 gigayears ago, from which we still see some remnants. This is very, very interesting. And I think the future still looks bright, in the sense that Gaia is still there, scanning the sky, detecting more sources that were too faint to enter these previous releases, but also improving the measurements. And sometimes it really makes a difference to have a reduced uncertainty by a half to make certain discoveries, as I have shown. And we expect for the first half of next year, DR3. So very, very soon we'll have for sure very exciting news. And I would highlight from this release, you can see this in the Gaia scenario of the data releases in the webpage of the Gaia pages. And maybe I would highlight for studies similar to mine, these 30 million radial velocities that will go from 12 magnitude as before now to 14, so 2 magnitudes deeper. We have 6 million, we will have 30. This is a very large increase that will allow us to explore even farther regions of the galaxy. So for sure, very exciting. And also these 300 million or about that classification and astrophysical parameters like log G, metallicity, derived directly from the spectra. And this again will allow us to separate populations and do this in a lot of detail. I have to mention also WIR, in which there's a strong participation of the Spanish community, and of course the survey will be done in Canary Island. And in the case I'm working with and related to the studies of the disk, we have this low resolution disk dynamic survey. It's part of the Galactic Archaeology survey, where we are looking specifically in the disk and gathering radial velocities for stars that are too faint to be detected by a Gaia spectrograph. So we will have radial velocities complementing Gaia proper motions for very, very faint stars starting up to 18 with very good resolution. And this is the footprint, or more or less the extension that we expect to cover in the galaxy. This will be the extreme and the farthest sample that we will have, with about 1 million measurements for individual stars. So again, great, and this will come quite soon, actually. Okay, and in the meantime, I've added this slide. Let me see the time. Good. In the meantime, in other galaxies. So I don't know, I didn't have time to look at the audience, but perhaps we have some extragalactic people here. And maybe you think, oh, this interaction between galaxies are nothing new for us. It's true. I'm showing here 2 pictures that I just found amazing with these 2 interacting galaxies and all these spiral structure that is a result of this interaction. But it's very easy to see here, not that much in our galaxy, of course, or lopsidedness seen in some galaxies. It has not even been investigated somehow if our galaxy has some sort of lopsidedness due to interactions. So I think it's good, and it's happening in this last years, that the links between galactic and extragalactic community are getting better, and I think we have a lot to learn from what is known about interactions already for external galaxies, and a bit the other way around, because we are starting to do similar analysis like this diagnosis that I shown from velocities in external galaxies. I'm showing here a recent paper. This is H-alpha emission, a measurement of velocities of this galaxy. And this, so the color, basically after doing some modeling of the inclination and so on, you see here all these patterns of vertical velocities in different locations. So some parts of the galaxies are moving up, some parts are moving down in velocity. And this we call a vertical correlation, and is exactly what is being detected in our galaxy. And now we are able to see these sort of things in external galaxies with this level of detail. And pointing, and finding what is the most likely reason, in this case, again, an interaction with a nearby galaxy. We have examples even of individual measurements of velocities in external galaxies by Gaia. This is the case of the LMC. I'm showing here a plot of the LMC colored as a function of BR, so the radial motions in and out. This is a plot from another performance verification paper of the early data registry of Gaia, led by Xavier Luri. And again, we see all these sort of perturbations and patterns from which we expect to be able to do this diagnosis and try to infer what are the processes, the dynamical processes ruling this evolution. And there is a PhD thesis going on in our team to investigate a little bit more that. And with this, I will finish with a very nice quote. I think this thing of galactic diagnosis has been going on for long, and we have here even a citation from 1972, from the Tomre brothers, who were the first to do a simulation of interacting galaxies with a computer. And they have this very nice sentence. We conclude that here, as in medicine, pathology seems instructive. And that is exactly what we are doing. But I think with Gaia, we are bringing this to another level. But again, investigating some pathologies of the galaxy to infer their past. And I think with this, I stop. And I'm happy to discuss, to answer questions, or whatever you want.
Perfect. Thank you a lot, Teresa. So now we can open the microphones for the audience. If anybody wants to ask something, you can just raise your hand. I can see a hand from Carmen Gallard. Please tell your name and your institution before talking. Thank you. Carmen, you can start.
Okay, I'm Carmen Gallard from Instituto de Astrofísica de Canarias. Really, really nice talk. Thank you, because it's always a pleasure to listen to something that is so understandable in the way you explain it, because it's not my subject at all, and I was able to quite follow it. So I would like to ask you some advice, okay? Because we are currently in the process of determining star formation histories across the disk. So we are working on a cylinder of 1 kiloparsecs radius around the sun, and up to 3.5 kiloparsecs from the plane. And we are just making a geometric dissection, in the sense that we are just doing like just slicing this cylinder parallel to the plane. So I wanted to ask, of course, I am totally aware that the stars that are in each one of these little tortilla de patatas, no? Which are parallel to the plane. They contain stars that have been in many different places, okay? But in the mean, I mean, they will be representative. At least we'll be able to provide a profile of the ages that there are as a function of Z. But the advice I wanted to ask was, would you suggest another different geometry, or what kind of kinematic analysis could we do in each one of these places, of these volumes, to understand better what are the populations there and where they come from? I don't know if my question makes sense. I mean, if there is any advice of if we could do it in a better way.
Well, yeah, in a better way, that is very hard to say. But first of all, I think there are two things here: star formation, radial migration. I mean, I'm not super expert on any of this, but I think maybe you depends on a bit on your goal. So first, I would say that perhaps studying these at different radii would be very, very interesting, because then you would somehow prove very, very well this radial migration, and for instance, burst by external galaxies, which I think, I mean, by interactions, which maybe dominate at outer radius. I'm not totally sure about that, because sometimes these perturbations really go inside the galaxy, and it's something that we are trying to investigate a bit with these cosmological simulations. So that on the one hand. If there's a better way to do this, I'm not sure. What I see is that it's going to be very complex to interpret, because it's very hard to tell what has been the movement of the stars.
We're assuming a kind of symmetry in the disk, but maybe from what symmetry as a function of Z. But maybe from what you see, we should expect something different.
Symmetry. Maybe no symmetry. I don't know. I really don't know, and it would be very interesting to see.
Yeah, okay. At least we will see.
I think the exercise is excellent, because it will tell you. I mean, first it will tell you what's the distribution, and if you see asymmetries, and if you see surprising things, I'm sure you will. And from this, inferring the exact processes will be a difficult thing, but of course, it's the first step. It sounds amazing. It sounds very, very interesting.
Yeah, no, the next step will be looking at it as a function of radius. Yes, okay. But we are first, it's just the first step.
No, it's good, and it's also quite local. I mean, you would need a more deep analysis to go even farther. So I think it's a very good first step. Yeah, I will think about it and see, and try to put all the pieces and see if there could be a way. But I think what you suggest is great.
Thank you.
Thank you, Karma. We have another question in the chat by Carlos Avia. He asks how you can distinguish between a star in the Milky Way and another one that is not in the Milky Way but in the Sagittarius galaxy, or probably the stream.
Yeah, in the Sagittarius galaxy, our selection comes from kinematics. So you basically see there is the dwarf that is detected, the core of the dwarf. So there is no doubt that this is the Sagittarius galaxy. And then by looking at the continuity of the proper motions, and by seeing that there is a sequence of stars doing this, then you immediately see it's related to that, and it's the stream. And it coincides with the location that you see in the detection of the stream photometrically, where you really see the overdensity of stars in the stream. So in this case, it's like this. For other galaxies, like the one I showed in the merger tree, you need the chemistry, because this is what allows you to be certain it has a different chemical evolution compared to the Milky Way, and be sure they come from other galaxies. But in the case of Sagittarius, it's simply with the kinematics, because the event is relatively recent. You can still see this coherence in kinematics, while for older perturbations, the thing has been totally phase mixed with our own galaxy, and this makes it harder. So you need to go to the chemistry.
Thank you, Tere. And we have now another hand raising that is by Mark Balotto-Sainz. Please, Mark, you can turn on your microphone.
Yeah, can you hear me? Good. Yeah. Thanks very much, Teresa. Excellent, beautiful talk. And it's a beautiful subject. Also very inspiring in showing how Gaia, a product of many years of preparation, is now providing the quality of data that is commensurable to the effort done in producing the whole Gaia system, which the Barcelona group is a big part of it. Anyway, beautiful topics. You know, I like dynamics. And let me ask you a couple of questions. A phase spiral, you said it's like a harmonic oscillator. And it's true. I mean, a harmonic oscillator.
Anharmonic. Yeah. Anharmonic.
Well, let me make my point. My point is that the phase spiral is a beautiful name, but many of us don't really know what it means. And you see the plot Z versus VZ, or even more complex phase space projections, and we're impressed, but we don't learn much from it. And I would my request to you and to your group is to complement your movies of galaxy interactions or galaxy processes with simple movies of these how simple dynamical systems perform in these projections, like radius, velocity, and harmonic oscillators or anharmonic oscillators. We would all learn a lot. It would be beautiful. So that's my request.
Okay.
Isn't it true that what's interesting is not so much the phase spiral, but the fact that the fact that you see a spiral means that there is some phase coherence between a big concentration of stars, which is what makes you come to the conclusion that something happened.
Yep.
That you injected a number of stars. No, yep. Something happens.
Yep.
So the interesting part is phase coherence followed by phase mixing.
Yeah,
right? Good. Great.
Yeah, and it is exactly what happens, right? So in this movie, there comes this small satellite, and part of the stars are displaced from the midplane. This means that they are suddenly in the same phase of the vertical oscillation because they are all up, right? So yes. That is exactly what you say. And they stay up for a while, but at some point, as you have different frequencies, because each particle or star will have different frequencies, then is when you start the phase mixing process. But it's true, the initial important step is phase coherence. So all orbits are moved to the same phase, at least in vertical oscillation. A similar thing can happen in the planar velocities. Yeah.
One question that came to mind when seeing the figures is that the phase spiral in principle could be in the accreted material or in the reaction of the disk to the accretion. I think you're saying it's at least to some degree it's the second one, but also there may be some injection of external material contributing to that pattern.
Not sure, because I mean, we know where Sagittarius is and where the stream of material from that accretion is, because it's still localized. And even though there can be other wraps that have not been detected yet, but they should be around the same position. So we don't expect yet stars from Sagittarius in the disk mixed up with the disk. Okay. We will in the future, for sure, they will be completely mixed, but not right now, at least from this interaction. But we do have some stars in the disk from other interactions as well. But these don't show anymore this phase coherence. So that is why we are certain that these are disk stars. showing this.
I have a quick question on the Sagittarius dwarf. When people who work on external galaxies and they do interactions, and people doing cosmological simulations, they tend to classify mergers as minor mergers, major mergers more than 30%, minor mergers 10%, and 1% accretion is almost unnoticeable. So where does Sagittarius fall in this?
It's a minor thing. So I think, and maybe Jorge can correct me if I see Jorge Peñarubia in the audience, if I say a wrong number, but I think now they are estimating 10 to the 8 solar masses for this galaxy. It could have been up to 10 to the 10 when it first entered the galaxy, and maybe it lost the material. So it's still a minor thing, since we are 10 to the 11 somehow. So it's it makes sense because, okay, I have a colleague that always tell me, oh, you're saying that there is this non-equilibrium and there is a big perturbation. Well, yeah, not so big, because we still have a disk, we still have a lot of coherence in the spiral. So it means that the perturbation is not that big. So that to completely destroy or unshape the disk. So this is a minor thing.
So 800 million years is a short time scale for merger.
Sorry, I didn't.
800 million years.
Yeah.
Is a short time scale.
It's very short.
It's very short on the context of mergers. A final question. I'm sorry I have asked so much, but I'm very interested in the topic. So when will it be that Gaia constrains lopsidedness in the Milky Way?
Sorry, what will be the Gaia?
When do you expect, or when can we expect Gaia to put important constraints on the lopsidedness of the Milky Way?
I don't know. This is some project that I just started, and I don't even found references. So I found one saying that the gas, which is in the very outer parts, shows some asymmetry that could be lopsidedness. And in external galaxies, it's seen that that gas and star. I mean, if gas shows lopsidedness, stars in the outer parts will show it as well. But I have not found any evidence of this for the Milky Way. So I thought, okay, let's try to look a bit into this. It will be very hard to detect because so there is predictions of how you would expect velocities to behave when you have lopsided, or when you have an elliptical disk, or when you have a bar, or when you have spiral arms. Most likely we have everything in our galaxy. So it's very hard to tell one from the other. So now we are in a project looking at only proper motions, because then we have more data, and with this trying to fit those models that predict how the velocity should be in lopsided, in elliptical, and for what we are finding is that none of them really fits alone, let's say, or maybe they are too simple, or the recent perturbation by Sagittarius is causing so much on top of this that it's very hard to tell. But yeah, I don't have yet a final conclusion. So, and I don't think that, okay, of course, when new releases come with Gaia and better data, this will be easier, but I think there is an underlying modeling problem more than that accuracy problem, let's say. And this will be harder. Of course, the better the accuracy, or the higher the accuracy, the better. But I think the challenge comes from the modeling part.
Not to mention the fact that you don't have the other side. You don't have Gaia data for the other side.
Yeah, for example.
Good. Thanks very much, Teresa.
Thank you, Mark.
Okay, good. Thank you. And we have a last question by Jorge Peñarubia. Jorge, you can turn on your microphone.
Hello again, Teresa. Thanks for your talk. I'm following you from talk to talk, but every time I learn something new. So I just maybe a comment, because I think what you show, the spiral pattern, is really beautiful, but I think it is at least I feel a little bit confused every time I see it, because I think it's not a local feature. It's probably going on everywhere in the Milky Way,
Yes.
with a different pattern, which is telling you something about the local dynamics of the Milky Way, and that maybe gives you an angle for the lopsidedness that you were that you were talking about might be another way to try to constrain it.
Yeah, I don't see a direct link now. What I do see, I mean, we have seen in the data that the global shape of the spiral becomes more flattened as you move with radius, and this is the signature of a not so strong restoring vertical force. And from this, you could infer, for instance, potential as a function of radius, something like this. And there have been some attempts about the azimuthal difference. That would be what would be related to lopsidedness, right? I don't know. I have to think about it, because this vertical thing, I mean, this spiral phase spiral is a vertical thing. And we see in simulations that sometimes vertical and planar things go separate. And they even have different mixing frequencies, right? So yeah, I cannot answer. It's very interesting though to see this azimuthal difference of the phase spiral. I'm not sure if it will be related to the lopsidedness and how.
Yeah. So may I add one final difficulty, which is the proverbial elephant in the room, which is
let's
the
add
LMC is going to perturb the Milky Way disk very strongly as well. So
yeah, for sure. And you've shown this. That's another ingredient that it's already shown that is necessary, for instance, to explain the shape of the Sagittarius string. And again, it's maybe the cause of the warp, which is also a vertical perturbation that will end up phase mixing somehow when the LMC disappears.
And this is just a message to Mark, because I think what we need is more dynamicists.
Totally.
Now we have the data, but certainly there is a lot of work in the theoretical.
Data is there. We are missing people trying to explain it and doing the modeling. I totally agree.
We have a lot of toys and we can play together now. So.
Thank you, Jorge. And we have a final question now, just a final one, by Emilio Alfaro. Emilio?
We don't
you can turn on your microphone, Emilio.
Okay.
Now.
Good morning, everybody. Thank you very much for your talk, but I am being too late for that, only for the discussion. So what's the problem of the timing? Was impossible to me to solve, because I have many of the questions and really are very interesting. Well, my question is that, I'm connecting with the Jorge's comment, is that I think we don't need, probably we need many more astronomers working in dynamics, but we have too many models and perhaps not so many data in some aspect. So now the problem, perhaps, to explain how this vertical, the 3D structure of the galaxy and the CEST phase space of our galaxy, is that the data are not extremely good, and despite Gaia is not so extended for many parts of the galaxy. And overall, because we have not so many informations or so much information also for the gas. For example,
I agree very much with that last point. I'm not sure I agree for the other, but okay, just.
Exactly. So my question is, do you have some information right now between what happened? There is some kind of correlation between vertical velocity and position on the and vertical height for the young star in the solar neighborhood. You have some kind of result for that?
I haven't looked at it myself, but there are some words looking, for instance, at the warp and how it's different when you look at old stars or young stars.
Mm-hmm.
I haven't looked at that. We have looked at how the phase spiral is in different age ranges, but to see this spiral, you need a lot of stars, and we don't have any good sample of good ages to see this, unless karma give it to me sometime in the future. So what we've done is beams in color in the main sequence, And then you see that the spiral is dominating mostly I mean, from young to quite old stars. You don't really see it at very old because then the frequencies are, well, I mean, there is a higher variation in frequencies. So it's more likely that you don't see any kind of coherence already. So it has already disappeared. Plus the older components are harder to perturb, let's say. So I changed a bit topic, sorry. But yeah, from this point of view of the spiral, we don't have large enough samples to do this assessment in particular. But there are other studies, like I said, like the warp or the average planar velocities for very young samples, and we are seeing some correlation with spiral arms, which again is expected. But
the correlation are limited to some spatial scale, no? So, for example, some.
Exactly. Yeah.
All right. Thank you.
And for the gas, maybe not okay for the young stars or related to that for the gas. There are observations of vertical perturbations in the gas as well, right?
Yeah.
And so this is something it's in my to-do list to try to see if they match what we see in the stars somehow, if they follow the same kind of oscillations in Z and radius. And this is to do.
Now, the problem with the gas is that, for example, some kind of interaction with the galaxy, like the Sagittarius dwarf, is very important, the ingredient of the magnetic field. So, for example, for the star, the situation is not so, so important, it's not so hard. But for the gas, it is very important because how the perturbation distributed over the galactic plane is very important, is very dependent on how strong is the magnetic field in the disks. So I think it is one of the problems we have in order to better define what kind of mechanisms are producing this, complicated extraction we are observing right now with this data.
Yeah. So and even worse because I have no idea about this. Magnetic field effects. Really out of my topic. So one other ingredient to take into account.
I think that Jorge was working with us, or Jorge, you was introducing magnetic field in some of your models?
No, God forbid, Emilio, that's too complicated for me.
Okay, thank you.
Thanks to you.
Okay, so we need to leave it here. And thank you everybody for the questions, and thank you, Tere, for the very, very nice talk and for accepting the invitation to give the IPARCOS astro-seminar. And with everybody, we will meet again next week, the same weekday, same time, with Guillaume Thomas from the IEEC-ICCUB. So thank you everybody for coming, and have a nice day and weekend. Thanks. Bye.
Thanks for the invitation and for the questions to everybody. Thank you.
Thank you. Bye.